So the P block here, we have 3 blanks, and this makes sense because as we learned in the early 20th century in physicists and chemists like Lewis and Pauling, is that electrons like to move in pairs, and then they bond in pairs. And so we cannot have 3 or 4 electrons occupying an orbit. So if we have a p block having 6 electrons potential, 6 squares wide, they will have 3 potential orbits because 6 divided by 2 is 3. And so this would be boron. So this would be actually the electron configuration of boron. We would have 1s2, 2s2, 2p1. This would be boron. That would be our electron configuration for boron. Now we move on to carbon. Okay, so let's look at carbon. So carbon is definitely going to be this. We moved 1 square over, and so it's going to be 1s2, 2s2, 2p2, and 2 plus 2 plus 2 is 6. Carbon's element 6. However, here we come one of our itty-bitty picky rules. That electrons try to distribute out to other orbits before pairing if they are in a sublevel. So we are not going to see this. That is violating our rules of quantum modeling of the atom. That's not going to happen. They must distribute into other available orbital paths next. So that would be the proper way to model the electron configuration and the arrow diagram of carbon. Okay, so remember that rule. So we're always going to seek our lowest energy state for our electron clouds. We will always fill from the lowest sublevel upward. We're never going to start up here or here. We always start here. We'll fill this up, then this, then this. But with each one, we try to distribute across orbits and half-fill orbits before we start doubling. So we move on to nitrogen. 2p3, that's nitrogen. Once again, we're spreading them out. There we go, okay? Cool, all right, and we add subscript. 2 plus 2 plus 3, that's 7. Element 7 is nitrogen. Move on to oxygen. Now we start doubling. We can start doubling, because we have half-filled all of our orbitals in our block, and that is oxygen. There we go. So here's our electron configuration for that. We move on to fluorine. We keep on doubling, okay? And then we finish our second energy level with neon. We are at a noble gas. One of the ways of defining a noble gas is that all orbitals are filled on an energy level. That is essentially what separates helium, neon, argon, krypton, xenon, and radon, is that all their energy levels have no unpaired electrons. They are as stable as can be. They've gotten that energetic stability. Okay, we'll just move on a little bit further. So we would naturally move on to sodium like this, and that would be sodium. Now here's a little catch though. Once these things start getting long, scientists will often, what they'll try to do is what is called the noble gas configuration. Instead of writing a long electron configuration, they'll basically replace all the previous energy levels with the most recent noble gas. And so the noble gas right before sodium is neon, and so here's a nice little shorthand. We call that noble gas configuration. Okay, and that works. So basically what you do is whatever electron element you're modeling, you just go to the previous noble gas and then just start, that was a little silly, and start on the last row, the last principal energy level. Okay, and so we can keep on moving here. This would be, of course, magnesium. If we're moving, if we're following your periodic table as we go, then I would go to aluminum. Okay, that's element 13. We move on to silicon. Once again, we have to distribute unpaired electrons across possible orbits. We would then, of course, go to phosphorus. Then we would start doubling. We would get to sulfur, 3p4. Then we move on to chlorine. And then we finally move on to our next noble gas, which is argon. Okay, so we have paired all orbits on an energy level. Okay, and as we wrap up our video today, so what we're going to have here is, notice that we're going to see a weird quirk. Okay, we've been pretty much just following energy levels as our principal quantum numbers. But once we get to the fourth energy level, things start getting a little bit different. Yes, we can start off with 4s1, okay, and that, of course, is potassium, and then we can move on to calcium, and then things get unusual. We enter into the world of the D block, and the D block has electrons that are energetically lower than the S, electrons in the S and the P block. The Y is beyond the scope of this video. You just sort of accept it on faith. And then we start filling up the D block before we go to the P block. And so this would, of course, would be scandium. Okay, beyond that, things can start getting a little bit irregular in that the sense that we could be having half-filled S orbitals in the S1 while we tag an extra one into the D block, or it may be an S2 and go to the D block. We're not going to really dive into that hard. That's, you know, and but basically, let's just pretend we've moved on to zinc. Let's just go all the way across to zinc here, and we fill this guy up. We've obeyed all of our rules, and then we come finally to 4p1, which of course is gallium, and we continue on from then. And so, once again, there's a lot of itty-bitty picky rules, but the basic principle is that we are trying to follow some very important ideas in quantum modeling for the electron cloud. And that is, first of all, elements are striving for their most stable, low-energy states for the electrons. We will always fill energy levels before we move to another energy level, the lowest possible. We will always fill sublevels before we move on to other sublevels. Within a sublevel, we will try to distribute electrons across orbitals before we start doubling them. And because no two electrons can have the same exact quantum state, these electrons have to have opposing spins within a particular orbit. Okay, so we're going to do an exercise real quick in seeing, does a configuration follow these rules? So once again, this is sort of a week of very itty-bitty picky little rules. We're not going to dive way into this stuff, but let's just do our next video. We'll kind of go into applying those rules under the principle of the electron cloud, seeking